In the name of Almighty God, I'm Master Sankosha, and today I want to go on lattice structure. A lattice structure is a three-dimensional periodic arrangement of atoms, ions, or molecules in a crystal solid defined by repeating unit cells. Overview of lattice structures. A lattice structure represents the ordered repeating pattern of particles in a crystal extending infinitely in three dimensions. The unit cell is the smallest repeating unit that captures the symmetry and contents of the crystal, and by translating this unit cell along its edges, the entire crystal lattice is formed. The geometry of the unit cell is defined by three edges lengths ABC and three angles alpha, beta, gamma, collectively called lattice parameter. Type of unit cells. Unit cells can vary in shape and complexity. Common types include simple cube, beyond centered cube, free centered cube. Center cube, simple cube or SC atoms are located at the corners of cube. Each atom is shared among 8 neighboring cells, resulting in a low packing efficiency almost 52% and a coordination number of 6. Body-centered cubic (BCC). In addition to corner atoms, there is one atom at the center of the cube. This arrangement increases packing efficiency up to 68% and coordination number to 8. Face-center cubic or FCC atoms are at the center and the corner and the centers of each face of cube. This structure has a high packing efficiency up to 74% and a coordination number of 12. Hexagonal close-packed or HCP layers of atoms are stacked in a AB-AB pattern, forming a hexagonal lattice with high packing efficiency up to 74% and coordination number is 12. Bravais lattice. At crystal systems, there are 14 unique Bravais lattices in three dimensions, which describe all possible ways to arrange points periodically in space. These lattices are grouped into 7 crystal systems based on the unit cell geometry: cubic, tetraangular, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. The combination of lattice type and crystal systems determines the symmetry and physical properties of crystal. Importance of lattice structure. The lattice structure influences many material properties including mechanical strength, electrical conductivity, optical behavior, and cleavage planes. Understanding lattice structure is essential in materials science, solid-state physics, chemistry, and mineralogy. Techniques like X-ray diffraction and computational modeling are commonly used to study and predict crystal structures. The summary would be, in a sense, a lattice structure is a framework of points representing particle positions repeated periodically in three dimensions. The unit cell is a fundamental building block, and variation in unit cell geometry and stacking lead to different crystal structures such as SC, BCC, and FCC and ACP. Each distinct packing efficiency and coordination numbers. Classification by summary. Crystal systems. The defining property of a crystal is inherent symmetry. Performing certain symmetry operations on the crystal lattice leaves it unchanged. All crystals have translational symmetry in three directions, but some have other symmetry elements as well. For example, rotating the crystal 180 degrees about a certain axis may result in an atomic configuration that is identical to the original configuration. The crystal has twofold rotational symmetry about this axis. In addition to rotational symmetry, a crystal may have symmetry in the form of mirror planes, and also the so-called compound symmetries, which are a combination of translations and rotation or mirror symmetries. Full classifications of a crystal is achieved when all inherent symmetry of the crystal are identified. Now I want to go through the theory. We start by presenting a linear stability analysis of the homogeneous solution x is equal to 0 to show that the transition point doesn't charge with respect to the single delay case. Let U2 denote an infinitesimal perturbation. Give the presence of two main timescales. We assume U2 is equal to U0 e to the power of alpha 0 plus alpha t divided by t multiplied by t, where alpha z is equal to lambda z plus I omega 0 and alpha 1 is equal to lambda 1 plus I omega 1, where complex numbers describing the stability over the two different time scales. Upon inserting these instars into the linearized version of equation 1, we obtain alpha 0 is equal to minus 1 plus e to the power of minus alpha 0 t minus alpha 1 multiplied by e to the power of minus alpha 0 delta j, where we have neglected 1 divided by t terms. Self-consistency requires lambda 0 to be equal to 0. This is a standard property of delayed models with a single variable, where all Lyapunov exponents scale as 1 divided by t. Additionally, in the large T limit, we are authorized to assume omega 0 t, which is almost equal to 2pm for integers. And as a result, we have I omega 0 is equal to minus 1 plus n e to the power of minus alpha 1 plus co omega 0, where co omega 0 is equal to ln e to the power of minus I omega 0 delta. In the uh, cumulant generating function, notice that chi omega 0 represents the correction of the single delay case. Alpha 1 to the power of s, alpha 1 is equal to alpha 1 to the power of s plus chi omega 0 expanding up to the second order in omega 0. We formally find chi omega 0 is almost equal to minus I omega 0 m1 and minus omega 0 to the power of 2 divided by 2 m2, where m1 is equal to delta j is equal to 0 and m2 is equal to delta j to the power of 2 minus delta j to the power of 2 are the first two generalized cumulants, so that we have a lambda 1 is equal to ln n minus 1 divided by 2 multiplied by 1 plus m2 omega 0 to the power of 2, and omega 1 is equal to minus omega 0. From the equations, we see that the omega 0 is equal to 0 is the most unstable wavelength, and the corresponding exponent ln n becomes positive for n is greater than 1, exactly as in the single delay case. In other words, in a first approximation, we see that a model with multiple delays behave as a single delay system, confirming the mean field approach. Having verified that a transition occurs for the same parameter value as for the single delay case, we now proceed by formally introducing the above-mentioned decomposition of the time axis t by writing write xt is equal to y sigma delta and xt minus tj is equal to y sigma minus delta j and theta minus y. In the vicinity of the bifurcation, it is convenient to write n is equal to 1 plus epsilon to the power of 2 and introduce the rescale variable theta is equal to epsilon multiplied by sigma minus nu theta and tau is equal to sigma epsilon theta. The introduction of a moving frame is dedicated by a later simplification of the final equations if the velocity nu is properly selected. By then following reference 15, we also expand the field in a power series Y sigma theta is equal to sigma. The lower boundary is equal to 1 and the upper boundary is infinitely epsilon to the power of k, z k, and zeta tau. This ansatz has been substantiated by numerically verifying that the time average field amplitude R is equal to time average field amplitude of xt actually scales as epsilon for different M2 is greater than 0 values. Each feedback term can expand as xt minus tj is equal to sigma lower boundary is k is equal to 1 and upper boundary is infinitely epsilon to the power of k and z to the power of k multiplied by zeta minus sigma epsilon delta j minus nu t minus epsilon to the power of 2 is almost equal to sigma. The lower boundary k is equal to 1 and upper boundary is infinitely zj k. By averaging over the feedback channels and expanding zk around zeta under the assumption that m1 is equal to 0, we find that zj to the power of k is equal to zeta to the power of k plus epsilon nu zeta to the power of k plus epsilon to the power of 2 multiplied by 1 divided by 2 m2 plus nu to the power of 2 zeta to the power of k minus zeta tau to the power of k and so on where the subscript indicates a derivative with respect to that variable. Analogously, the time derivatives of the field can be expanded as um, expression is equal to derivative of sigma y tends to sigma lower boundary k is equal to 1, upper boundary is infinite, epsilon to the power of k plus 1, z to the power of k, zeta and t. By finally including the expansion of the nonlinear term and equation in the various orders, we see that the condition for the linear terms in epsilon is automatically satisfied, while that for the epsilon to the power of 2 terms is z to the power of 2 is equal to nu z to the power of 2, which implies nu is equal to 1. The drift velocity is obtained. At the third order, we finally obtain the relevant equation which describes the evolution. Zeta tau to the power of 1 is equal to z to the power of 1 plus 1 divided by 2 multiplied by 1 plus m2 zeta zeta to the power of 1 minus 1 plus I zeta beta absolute z to the power of 1 to the power of 2 zeta I. This CG allocation reduces the noun expression in the case of the single delay, but is also valid in the case of a zero variance distribution as equation 2 when higher moments are different from 0. Equation 16 represents the main result of the theoretical part of this work. At leading order dispersion among feedback channels only modifies the diffusion coefficient d, for example, coefficient in front of the second special derivative of equation 16. Since a variation of d can be absorbed by rescaling the special axis, we can conclude that no qualitative changes of the overall dynamics are expected in the presence of the multiple delays, as indeed visually seen while comparing the panel of figure 2. On a more quantitative level, equation 16 implies that the spatial scale changed by factor square root 1 plus m2 introducing the correlation length SAC as a spatial distance such that SAC is equal to e to the power of mod. We expect that rho m2 is equal to SAC multiplied by epsilon m2 divided by SAC epsilon 0 to the power of 2 is almost equal to 1 plus m2. This prediction is truly investigated in figure 3 where the result obtained for different distributions which several M2 and epsilon values are reported. Recall that rho 0 is equal to 1 by definition. The different symbols refer to the different epsilon values. Solid blue straight line is theoretical prediction. We start noticing that in all cases rho m2 increases linearly with m2 for epsilon is equal to 0.10, the smallest value. Herein consider the slope is in a fairly good agreement with the theoretical prediction. See the full black dots. Upon increasing epsilon, the slope increases in a bit, suggesting that higher order terms here not considered are no longer fully negligible. We also performed some simulations for the two-delay distribution to validate the prediction that only the value of M2 matters. See the parameters in tab 1 and the M2 point in the figure 3. Figure illustrates rescale diffusion coefficient rho for different values of epsilon. See legend at the t is equal to 4096. The dashed line are guides for the eye, and the blue solid line is scaling predicted by the reference 60 in set A. Normalized correlation for epsilon is equal to 0.17 at the M2 values in the legend rescale by the correlation length as defined in the text. In set B, the enlargement of the negative regimes of M2 in the box, the M2 symbols are obtained from a two-delay distribution. See tab 1 for the M2 is greater than 0 case and the tab 2 for the M2 is less than 0 case. Other simulations are for a flat delay distribution, and a bare circle in B corresponds to distribution 2 with Q is equal to 1 and alpha is equal to minus 0.75. You see table 1 parameters and results for the examples in the case of two delay distributions for M2 is greater than 0. As already mentioned, M2 can also assume negative values. We have generated them considering suitable two-delay distribution. See table 2 for the parameters. The corresponding results The corresponding results can be seen in the lower left corner of figure 3, and in fact that they again confirm the theoretical prediction. The same data are presented also in the upper left instead, where one can also appreciate a difference among different realizations of the same variance M2. They are quantified by the error bars, which represents the standard deviation of the fluctuations among three different ways of obtaining a given M2 values. See table tab 2 for quantitative details. In practice, we see that for larger epsilon values around 0.3, the shape of the weight distribution matters, indicating that the more refined the theory becomes necessary. This sensitivity is a manifestation of the vicinity to the critical point M2 is equal to minus 1, below which the overall diffusion coefficient of the corresponding CGL equation becomes negative and cannot any longer reproduce the pattern generated by the delay model. Mathematically, from equation 9, we see that the omega transforms itself from maximum into a minimum of the stability spectrum, implying that additional terms must be included to ensure stability. For example, high-order special derivatives need be added to the CGL equation for equivalently higher-order terms should accounted for in a multiscale expansion to ensure even qualitative agreement. Nevertheless, we see in Figure 2a that the pattern generated for a negative M2 is equal to minus 0.32 is greater than minus 1 contains the same type of coherent structures as in the single delay case, just with narrower triangles. Table 2 plus trace parameters for the two Lattice distributions with M2 is less than the zero. You see omega 1, delta 1, omega 2 and delta 2 in order to further confirm the correctness of the theoretical predictions. We have investigated the entire profile of the autocorrelation function to verify it is independent of the delay. Once properly rescaled, various curves obtained for the same epsilon is equal to 0.17 and different values of M2 are reported in the lower right instead of figure 3. After rescaling of the spatial axes, they show a good overlap over a broad range of values, thus further confirming that the dynamics together is unchanged. As a last step, we consider the correlation length theta AC expressed in number of delay units such that the highest of the recurrence peaks visible in figure 1 decays by factor 1 divided by E. Our perturbative theory predicts that the timescale of the spatio-temporal dynamic is invariant in the presence of multiple delays. This can be qualitatively appreciated by inspecting the patterns in Figure 2. A quantitative numerical analysis for a flat distribution and epsilon is equal to 0.10 shows that the correlation length along theta passes from the theta AC is equal to 245.2 for the single delay, where M2 is equal to 0, to theta AC is equal to 248.9 for M2 is equal to 1.33, and to theta AC is equal to 253.2 for M is equal to 5.33. In other words, the variation is very small, 0.4% increase versus 255% for the spatial scale, substantially confirming the predicted independence of M2. Now I want to go through the conclusion sections. Altogether, we have shown that the presence of multiple delays, so long as the time scale of the dispersion is of the same order as that of the local dynamics, the overall behavior can be still described in terms of an equivalent PDE. Interestingly, we find that adjustment the coupling strength, the resulting amplitude of the diffusion coefficient may be tuned in both directions. For example, it can be increased as well as decreased. We have limited ourselves to considering a strictly real feedback, but there are no restrictions to extending the method to complex coupling with rotations, which would be very appreciated, especially in the context of networks of optical fibers. As symbol for deviations from the bifurcation of order is epsilon is almost equal to 0.1. The theoretical description is quantitatively accurate. Larger epsilon values lead to discrepancies, which indicates that the need to incorporate higher order terms. Preliminarily, studies suggest that many additional terms have to be included. We plan to further investigate the question in the hope of obtaining a relatively simple effective description. Finally, we remark that the dynamic depends only on the variance M2 of the delay distribution, thus the system is resilient, especially in the presence of a large number of feedback terms. Fluctuations of couplings, and delays have a very low impact, even more so considering the dependence on the variance consists essentially only in an adjustment of the pseudo-spatial coherent structures. Thank you so much for watching my tutorial video until the end. Today is the 13th day of June 2026. Time is 4:53 o'clock in the morning.